Hello and welcome to another video on basic fiber optics. Today we're going to talk about the trade-off between linear and nonlinear noise in a fiber optical telecommunication system. So in a previous video I explained how nonlinear noise builds up when a powerful signal is propagating through a fiber, but I didn't really go into detail with when this effect is large compared to the noise added by amplifiers. So in order to investigate this question, I've basically simulated the following setup multiple times using my custom implementation of the split-step Fourier method. Essentially, I'm launching the same signal into the same fiber with the same amplifier, but with different launch powers. And then I'm going to see how the signal-to-noise ratio of the output here changes. Now, this signal-to-noise ratio should basically scale the following way. We should have the signal power on top here, and the AC power and the nonlinear power in the denominator. And for various theoretical reasons, you can show that the nonlinear power should basically scale as the signal power cubed. So if you divide through by the signal power, what you find is the following expression with these two terms in the denominator. Note that if the signal power is very small, then the term in the blue box here, representing the nonlinear contribution, becomes negligible, and the signal-to-noise ratio will basically increase linearly with the signal power. But if the signal power is already very large, this fraction here will be small, and the signal-to-noise ratio will scale as 1 over p squared. So some kind of trade-off between these two effects must exist. That's actually what we see on the animation over here. So initially, if you have a very small launch power, you can see that the signal barely sort of sticks up above the noise floor. But if we increase the launch power, you can see it raises up quite a lot above the plateau here. Note also that this is on a log scale, so this pedestal here, representing the signal, is quite large compared to the noise floor outside. And if we keep increasing the launch power, we can see we get better and better signal-to-noise ratio. But at some point, the nonlinear noise, represented here by these blue sort of skirts, will begin to become more important than the additive noise of the amplifier. So right here is actually clearly more significant. And if we increase the power a bit more, it becomes completely dominant. So to investigate the exact trade-off, I basically graphed out the signal-to-noise ratio for different launch powers, as you can see right here. So initially, when we have very low launch power, increasing it seems to improve the signal-to-noise ratio until a certain point around 15 dBm, which is around here, where the nonlinear noise begins to kick in and reduce the signal-to-noise ratio. So just to make things really clear, this is a case where we have a very large amount of nonlinear noise. This is a case where we have a very large amount of linear noise comparatively. So what we can see is that somewhere in between, around 15 dBm, we have an optimal sweet spot power where these two effects, where neither of these are completely dominant. In that case, we get a very high signal-to-noise ratio. So you can imagine that if you're designing and operating a fiber optical network, it's very important that you determine the optimal launch power, because the amount of data you can send down a fiber link per second depends very strongly on the signal-to-noise ratio. So hopefully this sort of explains the trade-off between linear and nonlinear noise. Feel free to check out some of my other videos and stay tuned for more videos. Bye bye.